As we have previously discussed, this is very important. Taylor Swift is still on tour. So this gives us a whole new set of algorithms and data structures questions for us, which you should all be very excited about. Just like last time, I'm promising the same Taylor Swift tickets. So if you do very well in this class, maybe you'll be on your first class flight to Los Angeles to spend some quality time with T Swift. So do we remember from last time earlier in the semester who got the tickets? Who was it? Does anyone remember? Josh, you got a ticket?
Wasn't it like a bunch of us? Like we were all...
There were a few of you who got tickets. I don't quite remember. And so we should have some useful way to look up who the names of people and whether they had a ticket or not. So I want a data structure that's going to have the names of everyone in the class, and I can look up if they have a ticket, it'll give me a 1. And if they don't have a ticket, it'll give me a 0. So for example, if I look in this data structure and I give it the key Emlyn, I should be able to get out the number 1 because she has a ticket. However, Max, who's been underperforming for the last few lectures, haven't heard him say as much, he's got a 0 on the Taylor Swift map. So this gives us a couple of operations that we're going to require of our data structure. Can anyone think of the kinds of operations that I might want out of this? Ruben, you seem cheery today. You can have the first shot at it. Pass that back.
If a new student joins the class, we might want to insert them into this data structure.
So that seems good. The new students starting late, no ticket for them, but we do want to be able to insert them just in case they win later. Yeah, what other operations do we want?
Similarly to remove a student from the class.
Okay, add, remove.
And maybe to access the value of a student to see if they have a ticket or not.
Yeah, and we also need a way to look up or search our data structure for the student. So Ruben's just answered for us what functions it should have, and there are a couple of them. We want insert, we want search, which is our lookup, and we want deletion. Now we have a whole bunch of different ways that we could implement this abstract data structure. This abstract data structure we call a dictionary. And a number of you are probably familiar with it from your prior programming class or experience, where in Python, this comes built in. You have a map, or you have a dictionary type in Python where you can look up a pair of key that's a key and a value. So given someone's name, you can find out how many tickets they have or whether they have a ticket or not. And so these are our 3 operations. However, what is Python actually doing to implement this? What kind of data structure, what kind of algorithms is it using to facilitate this? Well, thanks to our hard work in the class so far, we have a few possible answers of what Python, or in C, we could do to implement these 3 operations. Again, this is an abstract data type, so as long as it has insert, search, and deletion, it's going to count as a dictionary. But the performance we get is going to vary based on what kind of underlying data structure we use. So for an unsorted array, insert is going to take O of 1. Ruben, you've still got the microphone. Do you want to say why insert on an unsorted array is always going to take O of 1?
Because we can just add an element to the end.
Yeah, we add it to the end. And what about search? What's the best kind of search we can do on an unsorted array?
Linear search.
Linear search. And then finally, deletion. How does this one work?
The same as search. We just have to search it and then delete it once we find out where it is.
And then we have a hole in our array. What do we have to do after? Yeah, we've got to move everything over. Remember from earlier in the semester, we had a whole bunch of students up, and then we had to copy them over one by one by one by one. Okay, Ruben, do you want to pass it over one way? You can pass it to Michael if you like. That's cool. Okay, Michael, what about our sorted array? Can you explain why we get these runtimes in a sorted array?
Well, like to insert at the to insert at the start, you have to copy over all the elements like to the right by 1 to be able to place that in. So that's going to take all the time for all the copies. To search, we just do binary search on a sorted array, so you get that log 2n or just log n generally kind of like search time. And then for deletion, it's kind of like the same case as before. If you want to delete like the first element or like any element afterwards, like on the average case, you're gonna have to copy everything back to the left to kind of stitch up the array, so all in time again.
That sounds good. Okay, Nick, you're up next. We now have our linked list version. Explain to me why we get these runtimes in a linked list.
Well, I think the logic's pretty much the same as that unsorted array, isn't it? So you just add it onto the end for linked lists when you're inserting, and then search, you have to scan through it all. So it's linear search, and then same with deletion.
Okay, great. And now we've got finally our new stuff. This is our worst case for binary search and our average case for binary search. So you can turn the mic on mute for the minute. For binary search, we had our insertion was O of n, our search was O of n, and our deletion was O of n for worst case, because we have the stick where we have to go all the way, we have to traverse through all the elements. It's kind of looks just like a linked list when you have a stick. And in the average case, we could have a balanced binary search tree, in which case we'd get O of log n for our operations. So this is not so bad. It does give us the abstract data type, the abstract data structure that we want. We can now do everything in log n time, but our question in this subject is always, can we do better? And unfortunately, I'm not going to answer that question for you today. You'll have to wait another week or two to get to it. But now that we have a way to look up who in the class already has Taylor Swift tickets, we're going to need some way of sorting out the real VIPs from the non-VIPs in the class. You know, the people who really deserve the remaining tickets. So we're going to do it on the basis of grades on assignment 1. So now we need a slightly different data structure because we're not just doing it based on when people arrive. It's not just like our queue before where if you arrive first you get a ticket. Now it's based on grades. And as students submit the assignment and as we grade them, we're going to need some way to make our data structure efficient so that the person with the highest grade is always the person at the front of the line to get the tickets. And if someone new comes and joins the line and they have a lower score, they should go further and back. And if they've got a higher score, they should go in front. So this is why a queue wouldn't quite be exactly what we're looking for, because our queue doesn't care about what the person's grade were or if they're a VIP or not. If they're first, if they arrive first, they're first. If they arrive second, they're second, etc., etc. So not quite what we're looking for. Instead, what we want is a priority queue. Now, a priority queue looks very similar to our normal queue before, except now associated with every person or every node that comes, there should be some value by which we're going to assign their priority, how close to the front they should be when we insert them. Now, what is the benefit when we remove from a priority queue if we've set up this order? Nick, you've still got the microphone. So we've got our priority queue where people, when they arrive, they get put in the correct place in the queue. So what does our remove do?
We'll take it out at the front.
It'll take out the front. And who's always going to be at the front?
The person who's got the most priority.
Yeah, the person who's got the most priority or the person who's got the highest grade. Now, we could implement this a few different ways because, again, it's an abstract data structure. So our trick in this class is going to be figuring out the best way to implement a priority queue, or at least a better way than the ones that we might have so far. So let's pass the microphone again to Oliver. Okay, so what is the stupidest version you could come up with to implement a priority queue? Each of these, the 3 operations we had before. There.
The dumbest version I could do.
That would still work.
Oh, jeez. Okay. All right. Is empty. Is it really a dumb way to implement is empty?
If it's a positive number, return not empty. If it's a 0, then okay. So let's skip that one.
Okay. Insert item priority. The dumbest way to make this.
Yeah.
That would still work.
Yeah.
What we could do is go through our whole queue, look through it all, you know?
So our queue doesn't allow us to look through it all. It just has look at front, look at back, and insert. So what about an array?
Okay, on an array.
Yeah, let's say we have an array, because a queue, we have restricted things we can do with it.
Okay, well, I could look through all of it.
Yeah.
And just check each priority as I go along. And once I find, you know, like basically one greater than that priority, I can slot it back and then move everything over. Or if it gets to the end and bam, it's the biggest, I can just put it in front.
So notice that this doesn't actually require the insert, doesn't require us to have created some nice ordering in our underlying data structure. It just has to be there. The tricky thing is that remove has to work, no matter no matter what your insert method was. So let's start with the remove one. So for your stupid version, how's remove going to work? Let's say we have an array, just a random array. How does remove work?
Well, Is it just removing the
We want to remove the thing that should be first, the thing with the highest priority.
Oh, well, I would do, if I had an array, I'm just going to assume it's just in there. I'm just going to search, if I'm doing dumbest way possible.
Yep.
I'll do a nice linear search over this array for the highest priority. And then I'd find that element. And then I would remove it by, if it's really dumb, I'm going to create a whole new array.
You can remove it. We've done linear search. We've looked at every element. We've found the maximum. We take that maximum out and we copy everything over. I think that's probably enough. Okay, but and if we're doing that, how does our insert work?
If we're doing that,
Yeah.
well, we could just...
What's the best version of insert for our stupid version of remove?
Okay, well, if our stupid version of remove is just to find the biggest one and pull it out, we could just find the... Wait, yes. Okay, so,
Yep.
in the dumbest way, if our remove is to find the biggest one...
Yeah. And now we're looking for the smartest way to do insert, given our way of doing remove.
And what are we inserting the highest priority, or just any...
You're just inserting a new item that's come along.
Oh, a new item has just come along.
Yep.
I could just... Can I just place it anywhere?
Yeah, you can place it anywhere. This is the simplest version of a priority queue. Every time you need to remove something, look for the maximum, and when you have something new, just put it there. And so we're going to get O of 1 insertion, because we just put it on the end, but we're going to get O of n removal, and it's also going to take a long time because we have to do all these copies. Now we have another naive version that's probably not quite as naive. This one is sort everything, which is going to take worst case, as we know so far, n squared, an average case n log n. If someone new joins, we're going to do n squared again. And then we're going to give tickets from the front of the queue, so we're just going to move from the front, and then we'll have an O of n remove. Or we could make it so that instead of descending order, if it goes in ascending order, and the person with the highest priority is at the end of the array, we can just remove that one item. So that would give us an O of 1 remove, but we would have to do O of n log n insert every time. So we've got a version which is O of n remove, we have with O of 1 insert. We've got a version which is O of n squared remove, O of 1 remove, but O of n squared insert. None of these seem great. Here's another improvement that we could try and make. So sort everyone in the queue. If someone new joins, fix the slightly unsorted queue by figuring out where to insert the new thing properly. And then at the last stage, we take out the highest element from the front of the queue and then fix the slightly unsorted queue if it's gotten, if the priority's gotten out of order again. And so our big question is going to be, if we do this, how long is it going to take to fix the queue every time? So we started off with sorted, and now we add something new, or we remove something. How long does it take to fix it up so that we get our sorted order back again? So using an array or using a linked list, which are two of our options that we've seen so far, we could get O of n insertion for an array and O of 1 from the back. Or for a linked list, we could get O of n insertion and O of 1 from the back. Again, still not really great. Plus, we have the O of n log n initial sort in the first place, so that's going to be a significant factor in our runtime. So even our linked list, one of our fancier data structures so far, was bad if we're adding items to a long priority queue. We've got this O of n insertion, that's not good, plus however much time and space it's going to take us to sort the linked list. So we have another data structure that we've seen thus far. We have a binary search tree. What about binary search trees as the basis for our priority queue? How are these? Well, unfortunately, the news is not good here either. So to insert something, we're going to get average case log n, worst case of n. If we are constantly keeping track of what the maximum is and just saving it in a separate variable, then we could actually get O of 1 worst case removal. But we're going to pay a cost when we do deletion, because when we remove something from the front, we're going to have to get the new maximum. And also with creation, we're going to pay a substantial cost. We're going to pay an n squared cost. So none of these seem quite what we want. And that's a long build-up to take us to the justification for why we need another new abstract data structure. This brings us to heaps. Heaps sit along with arrays, linked lists, and binary search trees and binary trees as a new abstract data structure. The rule for a heap is actually pretty simple. It's simpler than our binary search tree, which is just that the parent be larger than all of the descendants. So 100 is larger than 25, 100 is larger than 1, 100 is larger than 36. Great, that works. What about the other side? 100 larger than 19, then 17, then 3, then 2, then 7. But this also holds for subtrees. So any parent must be larger than all of its descendants. So if we look at the 19, 19 is larger than 17, it's also larger than 3, and 17 is larger than 2 and 7. So this is our heap property. Now, we can represent this heap in a couple of different ways. So we could use our binary tree representation with the pointers, but we could also represent it with an array. And so our rule for the array is going to be as follows. So the root of the tree is going to be at the 0th index. Any node's child are located at 2p plus 1 and 2p plus 2. So what's 2p where p is 0? 0. 2p plus 1? 1. And then 2p plus 2 is going to be 2. So our 19 and 36, which are the two nodes at the first level, let's say the root is at the 0th level, the two nodes at the first level are stored at positions 1 and 2. Now if we want to get the children of 19, 19 is at index 1, so 2p plus 1, that's 3, and so we can see that 19's first child is at 3, and 19's second child is at 4. So just like you can get the children of a node by doubling it and adding 1, you can reverse that to get the parent of a certain node by doing n minus 1 on 2, where n is the index of the child. So that's just a different way of implementing our abstract data type. We can do it with pointers and represent it and draw it out that way, or we can implement it using an array. Now, just because we draw the graph version doesn't mean that we're using the pointer version in C. Both of these two representations are equivalent. It's still the same data structure. What matters is not how you draw the picture that helps you conceptualize the links between the different elements. What actually matters is what code is driving it. Now, for some of these examples, I'm going to try and both do the array and the graph at the same time, so you can see how the two are related. Now, the great thing about our heap, and this is a binary heap because every parent has how many children at most? 2. Great thing about our binary heap is that we have now improved on all the operations that we really wanted for our priority queue. So on average, we're going to get an O of 1 insert with a worst case of log n. Our find maximum is always going to be O of 1. Our create is going to be O of n, and this is where some of the real magic is, and we'll do a proof of that. And our delete is going to be log n. So this is much, much better than our binary search tree, even though we're still drawing it out by this kind of representation. Now, this should be an easy one. Oliver, do you want to pass the microphone in some direction? So, okay. How am I going to find the maximum in a heap? How do I remove let's just start with find max.
It's just basic loop through.
Do I have to loop through? We know that the parent is always larger than all of its children, and that we store parents earlier on in the array than their children. Yeah, the first element. A0, if our array is called A0 is the largest element. So our find max is always going to be O of 1. Now, even if we're using the pointer representation, we can do the same thing. It's the very first element of our tree. However, all of the benefits that we just talked about over here, these binary heap benefits, you're only going to get if you implemented an array. Now, there are fancy ways of doing some stuff with pointers to optimize it, but really, these benefits you get by using a particular implementation of our abstract data type. So you can turn it on to mute again for a second, and maybe we'll get back to you in a couple minutes. So our max heap rule and our min heap rule are slightly different, but they're conceptually the same thing. In the data structure that we saw before, it was the largest item at the top, but we could build a version of it where it's the smallest item at the top. And the only difference is in our implementation, we're going to flip some of the comparisons. So the max heap rule is that the parent is larger than all of its descendants, and the min heap rule is that the parent is smaller than all of its descendants. So relatively straightforward. Hopefully, if I've done my slides right, we're only going to be looking at one of these today, and that will be the max heap. But to make a min heap, it's quite similar. Now, another fun thing about heaps is they are a favorite problem of algorithms interviewers if you're interviewing for a job interview at places. So the other comparison that we could make is to compare it to our binary search tree. So our max heap rule is that the parent is larger than all of its descendants, and this is distinctly different from our binary search tree rule, which is that the right child is greater than the parent that is greater than the left child. And notice that the max heap rule actually applies to all the descendants and not just to the children. So even while you get a partial ordering with a binary search tree, you're going to get a different partial ordering with a max heap. Another thing that's important to know about heaps is that every path that you can follow, assuming no backtracking on a heap, is going to give you a sorted list. Now, it's not going to be the sorted list of all the elements, because if you take one path, then obviously you haven't seen all the elements not on the path. However, if we do try and follow this, and let's see if it works, 10, 14, 18, that's a sorted list, right? Let's try 10, 14, 17, also a sorted list. 13, 15, 30, also a sorted list. So this property is also going to end up being very useful for us. So we've talked a little about our array representation already. And here's another slide mentioning it. So for our array 0 to n minus 1, so n elements, the two children are located at 2i plus 1 and 2i plus 2 for some index I, and the parent is just the reverse. One other key feature of our heaps is that they are implicitly balanced. What this means is that we can't get this stick property. It's impossible to get a stick from a heap. It's impossible to get a stick from a heap. A heap is always going to look relatively balanced. If you imagine that the nodes have some physical weight to them and you put them on a scale, it's going to be as balanced as it can be, with the exception of the last row, the last set of nodes. So we've talked a whole lot about the virtues of this thing. Great. I've shown you a picture of it, but how do we actually build one? How do we do our operations on it? This requires talking about two subroutines, sift up and sift down. So let's go through these one by one. Then we will do our insertion and our deletion and our construction of the heap. And then hopefully today we will finish off with a little bit of magic, and I will give you a worst case of nlogn sort. Remember, we've done a whole lot of sorts thus far, but we could only get worst case n squared. At the end of today, hopefully we will get to nlogn. So starting off, we have our sift up. Our function is going to take in the array, that'll be a new value that we want to add in x, and the number of elements in our heap so far, n. The basic idea here is to check if the element that you want to insert is larger than its parent, and if it is larger than the parent, then what do we probably want to do? Yeah, Bruce.
Oh, it's larger than the parent. We make it the parent.
And then what's going to happen to the parent? It becomes the child. So we're going to want to do a swap. The basic idea here is you put the node that you want to insert on the tree, and while the node is while you've violated the heap property, you swap and keep swapping up with the parent until the heap property is no longer violated. So let's turn to this and see if we can do it with the picture. Now, please, if I make a mistake, which I might with this one, yell it out, because otherwise we'll all get confused for longer. So let's say we want to add the value 260. That's a good one. Okay, so where is the obvious place to put this? If I need to put it in a free place to start off with, where's the obvious place? So I could put it as a child of 252, but this is a binary tree. And so we only have a left and a right pointer, and we only have space for two children for every node, even in our array representation. The next place that we have two free places are there and there. And so let's just take the first one along. Let's put it there, 260. Now, is the heap proper? Do you want to take the microphone, given that you're already helping us? So is the heap property violated? What was the heap property again? Is the parent larger than all of its children? It's violated. And so what did Bruce just suggest we do? At least, yeah, we could swap it. So let's put 131 in there and 260 in there. Okay, is the heap property still violated? What about these two? Is the heap property violated? Is the parent larger than its child? It's not larger, so that the heap property is violated, and so what do we have to do? Swap again. Okay. 52, 260. And now, is the heap property violated? Not violated. Great, so we're done. Anyway, so we're done. We have swapped, we've inserted our new element to the first place free on the tree. And then we've repeatedly checked if our heap property is violated. If it's violated, we do a swap. And then we keep repeating this until we now have a correct heap again. So let's restore our tree. And now we're ready to try and do deletion. So the code we had here just does exactly what we said before. So start off at location n, and if we have n nodes, the last index of the array that's already full will be n minus 1, because remember we have to account for element 0. So we start off by putting the value x at the very last possible place, which is at location n, and then while the heap property is violated, swap up and then move and repeat the same operation on the parent. So when we do deletion, our trick now is going to be to always delete the root in a heap. Why are we always deleting the root? You want to pass the microphone back to help Nadine from falling asleep. Remember, we're working with a priority queue. And so we always want to take out the maximum value. So why are we always going to delete the root in a heap if this is our goal? What's value is always at the root of a heap?
Largest.
The largest value. So if we're doing our delete, which value are we always removing? The largest value, which is at location what in the array? 0. So for our deletion, we now know that we're always going to delete the 0th element. And we're going to do it roughly as such. So the first thing we're going to do is move the last element that currently exists on the tree to the place where the root was originally. Once we do that, do we need to keep track of the root anymore? Bronson, you've got the microphone. So assuming that we're deleting the root, say we've swapped the very last thing in our heap with the root, do we need to still remember the root?
Do we still need to remember the old root?
Yeah, the old root. No, we don't need to remember it. We're just deleting it so we can throw it away. And so you'll notice that's what we do here in the code. We set the new root of the heap in position 0 to be what used to be the last leaf on our heap. And then we call a subroutine sift down. And this is where things start to get a little trickier. Okay, so our sift down is going to work very similar to sift up. It's just going to do it from the other direction. So what we're going to do repeatedly is check if our heap property is violated, but instead of checking it from the last leaf to its parent that we've just put on, we're going to check it with the current parent and its children, and then swap it appropriately with its children. So let's try to do this on the iPad, and that'll make it a little clearer. So here we have our array again, and Bronson, you're going to walk me through this. We're going to try and get it intuitively, so I'm not going to give you all the steps ahead of time. So we want to remove something from our heap. What are we going to remove? We're going to remove the root. And what did I say we do to remove the root? You answered me this a minute ago. To remove the root, let's go back to our slide. What do we do to remove the root? It's up there. So what's position 0?
So you set the first element of the array.
To be? If there are n elements in our array, what is n minus 1? That's the last element. I see you've woken up now. Okay, so that's our last element. So what we do is we take what used to be our last element and we make it the first element. So cross out 3, 2, 3, we write 1, 1, 1. And that's the same as over here, crossing out 3, 2, 3 and writing out 1, 1, 1. And again, remind me, you said this before, why don't I need to save the value 3, 2, 3? Yeah, that's the one we're deleting. And so what we're going to do, we'll decrement n when we return from the function because we've just deleted something. And then this whole area, that'll be outside the bounds of our array now. Okay, so now what we want to do is again check if our heap property is violated at every stage. But unlike last time, now which links am I going to check? Before I was checking from the bottom up, and now I have to check, what have I changed?
We have to check from the top up because you've changed the root.
Yeah, I've changed the root, so I have to check from the top down. Okay, so let's see. Is the heap property violated with the left node? Is 111 bigger than 252? Is 111 bigger than 252?
No.
No. Is it bigger than 282? No. Okay, so we're going to have the rule that whenever we do this, we'll always go with the bigger of the two children. So let's do the same thing that we did with the other sift. What did we do with the other direction sift? What did we do? Swap it. Okay. So we'll put 282 there and 111. Now what do I do?
Repeat. I guess starting from 111.
Yep, 111. And what am I going to do?
Compare it with its descendants.
Compare it.
And 222 is larger, than 111. So is 141, but 222 is larger than 141.
So I could put 222 and 141. And I haven't been remembering to keep track of it with the array down the bottom, but we can... 111, sorry. 111. So if we were to do those swaps over here, let's rewind a little minute and then we'll fast forward. Okay, so what we did is we swapped 111 with 282. So we compared 111 with its two children. So that's 2i plus 1 and 2i plus 2. When we saw that we wanted to make it a child of, when we wanted to swap it with 282, we swap these two array elements. We swap this array element and that array element, or we swap that array element and that array element. Then we are going to compare index 2 with 2 times 2 plus 1. So 2 times 2 plus 1 is that, and 2 times 2 plus 2 is that. And so then we're comparing with 222 and 141, which we saw that we were comparing before, and then we make the swap as before. So that's how sift down works. Let's look briefly at the code and just see if we can spot those features again, the same features that we just worked through. So assuming we have an element at index p, the first child is located at element 2p plus 1. We want to have a check to make sure that the child actually exists, and we do this by making sure that the value of the child is less than n, because we know if we've hit n, then we're outside the bounds of our heap. Okay, so assuming that the child exists, then we check if the which of the children is bigger, and we also check that the right child exists. And then we are comparing ourselves with the larger of the two children. And if we are if our comparison fails, or if our comparison is true in this case, then we know we have to do a swap, and we just recursively call sift down on the remainder of the tree. Yes, have I made a mistake in something?
Oh, I was just wondering, at some point, do we have to decrement the value of n?
Yes, so one thing I was about to mention this that I've excluded from both the insert and the delete function is dealing with incrementing and decrementing n. So if you were actually implementing these in a real C program, you'd want to make sure that inside these functions you're using a pointer to n, and then you can increment it and decrement it inside the function. Otherwise, this implementation, this sketch that I have here, assumes that the incrementing and decrementing is being managed in some other like higher function. But yeah, great to point that out. So our build heap works pretty simply. We start with an array of objects that's not in a heap yet, and the number of items in our array. And all we're going to do is repeatedly call sift down. And we know that each time sift down is going to put one more element into place. And so if we repeat it once for every element, then we're going to result in a correctly constructed heap where the property is true for every node. This, after all that work, we are finally at our exciting worst case nlogn sorting algorithm. And you might be surprised by how simple it looks. So here is our corrected heap sort. We are going to build a heap as our first step. And then for every element, once we've built a heap, we are going to swap out we are going to take in an unsorted array. We're going to build a heap out of it. And then for every element in the heap, we are going to swap the last element in the heap out and put it in the root, and then call sift down. And we do this repeatedly, and once we do this once for every element in the array, we are guaranteed that our overall array is sorted. And how do we know this? We know this by virtue of the heap property and the fact that each time we are repeatedly calling and removing the last item in the array, and we're getting a partially sorted array. And as we go, just like our other sorts that we've seen, we are moving things from the unsorted portion of our data structure into the sorted portion of the data structure. And I'd encourage you to actually go and write out these steps one by one and see that it really does work. So I've told you that this is nlogn, but that doesn't seem entirely intuitive, because after all, our build heap had to call sift down a whole bunch of times. And if we think about how high our tree is and how many possible times we could do sift down could run as high as the height of the tree. And the maximum height of our tree is log n, is log n once we've put all the nodes in. And so that gives us log n for sift down, and we're running at nlogn there. And then once we have done that, we're doing nlogn again. So, yeah?
Yeah, but it's multiplied by like a constant, right?
This is going to be the kind of the trick. So in our heap sort, we're going to get build heap, and build heap we're going to try and run in O of n. Then we have a portion in our heap sort where we're removing the items one by one and then calling sift down, and we also need this to be nlogn if the overall runtime of heap sort is going to be nlogn. And this might be a little unintuitive, but we will see as we actually evaluate it what the worst case runtime is. So let's break up our program into two separate portions, because obviously we have the build part that looks a little different from the heap sort, the main part of heap sort. So build heap is going to run sift down n on 2 minus 1 times, because we're going to do that for everything but the root node. Then we are going to run our sift down thing. Sift down is going to run that little bit in the middle h times. So let's try and do a simple proof that actually shows that we can get our heap construction in O of n. We might naively assume that to build a heap takes nlogn time. After all, looking at its construction, we can see that we run the main loop n on 2 minus 1 times, and then if we're swapping things down using sift down, and we have n nodes in the tree, then we have a maximum possible of log n swaps. That is, the height of the tree is a maximum of log n, and therefore we can do a maximum of log n swaps from the top to the bottom, the height being h. However, there's some subtlety here. n is actually the total number of nodes that we're going to have put in the tree when we're done constructing it. However, until all the nodes are there, the height of the tree is not yet log n. So sift down is not going to take a full log n to run every time, and therefore the loop isn't going to take n log n. That's not a tight bound. It's just a big upper bound. When we've only put one node in so far, we can't do the log n swaps. In fact, there are no swaps at all. There's only one node in the tree. When we've got two nodes in the tree, at most we can do one swap, swapping the root with its child. And so in the proof that follows, we're going to do a summation that shows that accounting for the fact that we're adding nodes one by one, and we're adding them to the bottom of the tree, we're going to end up with a total of O of n runtime, a much tighter bound for our heap construction. So let the bottom of the heap be level 0 rather than the top. So if I was going to draw that out, let me get to a nice picture of our heap. If I was going to draw that out, let this be level 0, that be level 1, that be level 2, and that be level 3. Now, how many nodes can I have when the last level isn't completely full? Josh, I think you might have an answer for this one. So if I have a heap which has the last level completely full, how many nodes will I have at most in my last level, assuming that I have n nodes and that the height is h? And let's say the current level is, h is the height of the tree.
Which is 2 to log n, which is...
So let's just leave it at that for the minute. We have maximum of 2 to the h nodes at that level. How many do I have at 2 to the h minus 1? Oh, sorry, at h minus 1. At level h minus 1, how many nodes do I have? I have 2 to the h minus 1, and then 2 to the h minus 2, and then 2 to the h minus 3. And so we can represent that minus as an I, and I ranges from 0 to 3 in this case. Where 3 is what value? How can I represent 3 if I know I have n nodes? I have n nodes. Yeah, Max has got it. So
Then, if you plug that in Meta with some of the others, does that mean bottom level has maximum n nodes on it?
2 to the...
N is n, right?
Yeah.
And half of the bottom level of if it's 1.
Yes.
Okay, yeah.
Okay, so we're good. So Max has said that this number, its range is from 0 to log n. That's how we get 3. Okay, so that takes us to the next step in our proof. We have a maximum of 2 to the h nodes at our last level. And we know that therefore n must be at least 2 to the h. That seems relatively unobjectionable because we know that we have 2 to the h nodes in the last level. So our total number of nodes has to be higher than that, right? We also know from our picture just before that we have 2 to the h minus I nodes at level I, which means at any given level we have maximum I swaps down for each node, because I is how many levels we have, as what level we're up to. And so if I is, say, 2, then we're going to have maximum 2 swaps, 2 levels that we can go down. Let's write this in a summative notation. And so for each of the nodes at each of the levels, so this gives us how many swaps we can do for a given level, and how many nodes exist at that level, because we can't swap down a further point than the number of nodes we have. We know we can't do that. And then we're going to do this all the way from the 0th level, which is the level with the most nodes on it, all the way up to the top. So going back to our picture, for each node on this level over here, what is the maximum number of swaps of sift down that could be done? Are there any sift? Can we go down any further than the last level? No. Okay. So what about here? We have 2 to the h minus 1 nodes, and each of them can be sifted down at most once. For here, we have 2 nodes, and each of them can be sifted down at most twice. And at the top, we have 1 node that can be sifted down at most 3 times. So this gives us our formula over here. We have a certain number of nodes at each level, and each of those nodes can be swapped down a maximum of I times, and all we have to do is sum this up for the total number of levels we have. We're going to count up the number of swaps that can be done for each node at each level. And now let's simplify that out with a little bit of maths. It's not too hard. This is high school stuff. And so we end up getting 2 to the h plus 1 maximum number of swaps. Now remember, I had this on a couple slides ago. I said that n is at least 2 to the h, which means that 2n must be bigger than 2 to the h plus 1. But I just said before that the maximum number of swaps we can have is 2 to the h plus 1, which means that 2n is bigger than 2 to the h plus 1, and therefore our runtime is O of n. That is the maximum number of swaps we need to do when constructing our heap. So if we go back to our heap sort, we now have build heap, which we know from just now takes O of n. We know that sift down takes log n once all the nodes are in the tree, and we do this n times. So we get n plus n log n, and we get the final runtime of heap sort, which was, worst case, n log n. Because n log n is larger than n. It's the term that dominates, so we throw away the n, and we get an O of n log n sorting algorithm. Why? Our build heap was O of n. Remove max is always going to be log n, and assuming that we have a heap that we've built, to get something sorted, if we know that we're always going to take out the biggest item from our priority queue, one way to sort something is to have build a priority queue, and then take out the first element from the priority queue, take out every element like that, and just put them in an array, and then you have a sorted array. And this is another intuition behind understanding why heap sort works. It's basically this idea of fast priority queue construction. Okay, we're ready to do heap sort now. What our process is going to look like is swapping the element at the 0th position, that is the root of the tree, with the one at the very end, and then marking the end of the tree as already sorted. And we'll see how this works, and if we repeat this process, we'll eventually end up with a completely sorted array. So the first thing we're going to do is swap 323 with 111. 323 is the largest item in our array, and so if we swap it with 111, we are going to end up in a situation where the rightmost element of our array is in the correct position. Now, I'm not going to write 111 in this position over here yet, because we're going to have to do some swaps to fix up our heap. Now, 323 is no longer going to be considered for the purposes of our heap sort algorithm because it's already in the right position. But now let's figure out where 111 goes. So 282 is the bigger of these two elements, so 282 is going to swap with 111. And then after that, 222 is the bigger of these two elements, and so we're going to swap 111 with 222 after that. So let's fix this up. We're going to get 282 at the root, 222 here, and 111 here. Now let's fix up our array representation. So 282 is the new largest element. We have 222 over here. And then 111 where 222 used to be. Okay, are we done? No, we only have our last element in correct sorted position. So let's do the same thing again. Let's remove the root and swap it with the last element in our heap. So that means swapping 282 and 66. So 282 is going to go here, and we'll temporarily put 66 here, but now we're going to have to do a few swaps. So out of the two nodes that are children of 66, 252 is bigger. And out of 252's two children, 131 is bigger. So 66 is going to end up over here. So let's put that in. 66 is going to go there. 252 is going to be the new root. And 131 is that node in the middle there. Okay, let's fix that up in our array. So 282 has been moved all the way to the end, and now it's in the correct position as well. See, we have 323, then 282. 252 is the new root. Its first child is 131. And then 131's second child is 66. Now note that even though right now you can see this 282 here being larger than 252, that's not a problem because we're now considering it to be outside of our heap and it's actually been sorted. It's at the end of our array. So we're essentially just doing repeated removal of the largest element, putting them on the far side of the array, and then continuing on. And if you keep removing the largest element over and over, you get a sorted array. So here we go again, and I'm just going to do this as quickly as I can. So 141 and 252 swap. But of course, that's no longer in our array anymore. And now these three elements are all sorted, but we've got to put our 141 into place. And our 141 is going to end up in here. So 141 has been swapped just with 222. There we go. And 111 is still part of it. So 222 is the new root. Okay, same thing again. Remove 222 and swap it with 111. And now this is no longer part of our tree. Now we have to figure out where to put it. It is going to swap with 141. Do the same thing again. 141 swaps with 66, which is now the last one. And now we have to put 66 into the correct position. So that is going to swap with 131 and with 121, making 131 our new root. But of course, that 66 isn't going to stay there for long because it is getting switched out with 131. So 131 goes over here. 121. Remove the biggest, which is 121. Swap it with the last node, which is 111. And now all of these items are in sorted order. Now we only have one swap left after this. So let me just write this last one in. 121 gets crossed off. 111 is here. Remove the largest item, which is 111. Swap it with the last one, which is 66. And do it on our main tree so you can see that. Cross off 111. And now we've only got one node, so we can't swap it with anything. So let's cross it off as well and check our final array. There you have it, an nlogn worst case time sort. And this takes us to our heap sort code, and that'll be the last thing that we will do today. So we have our sift down, which is roughly what we saw before. In fact, there are very few differences. The main difference here is that we're using a CMP function that we talked about earlier in the week. Build heap is only a couple of lines as we had it before. Heap sort, also amazingly simple. And then here is our main function. We're going to run some tests on it. And there you can see we have heap sort that works perfectly well. Now, one thing that I would like you to do at home is download the heap sort implementation and also sort scaffold that you'll need. And once you have both of those, compare them to the other sorts that we've seen thus far and see if you can actually see the difference between them. Now, why might we not see heap sort being better than our other sorting algorithms after I just said that it has really good worst case runtime? Who's got the microphone at the moment? Where did it end up? Yeah, Owen, why might we, let me say that again. So if I got you to run this heap sort implementation, and I got you to run one of our other sorts, let's say quick sort, why might I see that quick sort actually does better, even on random items? Yeah, so sorting is somewhat dependent on the kind of data it gets in. And more than that, we know that heap sort is only worst case nlogn, and even though it's average case nlogn as well, we don't actually know the constants out the front. So what we actually want to know when picking a sorting implementation for our real world data is what is it going to end up being on average on the kind of data that we're looking at. So with that, we've got sorting in worst case O of nlogn, and I look forward to seeing you next week for some more sorting adventures. Thank you very much.